Well, in this fuel cells and batteries course, we have been discussing about PEM fuel cells in the previous lectures, and we have seen what are the alternative membranes for naphthalene membrane in the previous lecture, right? So in this lecture, we are going to discuss about high temperature fuel cells. What we have discussed earlier was PEM fuel cell, under which there are two subcategories: low temperature PEM fuel cells and high temperature PEM fuel cells. And then we have seen some what are the properties of membranes, or what are the alternative membranes that have been researched, what are the research trends associated with the new membranes that has been developed for high temperature PEM fuel cells have been discussed. Okay, so in this lecture we are going to discuss about high temperature fuel cells, under which we are going to have moderate temperature fuel cell and high temperature fuel cell. So molten carbonate fuel cells will be categorized as moderate temperature fuel cell, and solid oxide fuel cell will come under high temperature fuel cell. But these two together are operated above 200 degrees Celsius, so we are going to classify them as high temperature fuel cells. Okay, so particularly this molten carbonate fuel cell is a high temperature fuel cell, which is operating temperature is above 650 degrees Celsius. Okay, so in comparison to solid oxide fuel cells, this molten carbonate fuel cells also have some advantages, like there is a flexibility in using fuel for this particular fuel cell, and the reaction kinetics are supposed to be faster in this case. However, there are some demerits associated with it, because since we are operating at high temperature, there is corrosion associated problem is there, because we are using molten carbonate electrolyte. Okay, so we are going to discuss about molten carbonate fuel cells in this lecture. Ready? Okay, before getting into these high temperature fuel cells, well, let us see the motivation why these high temperature fuel cells are significant. If you look at one particular chemical industry, that is cement industry, in India, we have several cement industries. India is one of the major producers of cement. Okay, and if you look at any cement industry, actually they produce 0.9 pounds of CO2 per every pound of cement is being manufactured, because this cement industry contributes around 5% of global anthropogenic CO2 emissions, which makes the cement industry as an important sector for CO2 emissions mitigation strategies. That means if you want to reduce the CO2 emissions, then we have to look into the cement industries with greater interest. Okay, because in cement industries, CO2 is being emitted from several components in the plant. Okay, for example, from the calcination process of limestone, from the combustion of fuels in the kiln, as well as from the power generation units. In all these places, CO2 is being emitted in the cement industry. Okay, actually the cement is only a fraction of the constituents in a concrete manufacture. So manufacturing a cubic yard of concrete, about 3,900 lbs, is responsible for emitting around 400 pounds of CO2. So that is the case with cement industries. And in particularly in India, if you look at, we are the second largest producer of cement in this world. Even when the cement manufacturing was deregulated in 1982, so Indian government deregulated the cement manufacture. So there were large investments from Indian as well as foreign investors into this Indian cement industry. So because also these cement industries provide around 20,000 people job it is providing per million ton of cement is being produced. How much million tons of cement is being produced in India? If you look at the government data, so it's worth US dollars of 5.28 billion between this April 2000 to March 2018. So as per our IBEF data, we have been producing around 502 million tons of cement per year. And this actually some addition of this cement capacity production is being done every year. Almost 20 million tons per annum is being added. So it is a projection that by 2025, India's cement industry is expected to reach an 550 to 600 million tons per annum of production, cement production, particularly grey cement production. And if you look at who are those people who are producing the cement in India, you can see that the Aditya Birla Group, Ultratech Cement, is the largest manufacturer of grey cement, ready-made mixed concrete and white cement in India. So these are the top 10 cement production based on the turnovers or based on the production capacity also. You can see here the list. So we have Ambuja Cements, ACC Cement Limited, Sri Cements, Dalmia Cement, Birla Corporation Limited, India Cements Limited, the Ramco Cements Limited, Orient Cement Limited, Heidelberg Cement India Limited, which is a subsidiary unit of a German company. Okay, so these capacities, you can see that there is 100 to 5 metric ton, million tons per annum is the capacity distributed between them. Okay. And if we want to look into this net zero carbon emissions target, because the current trajectory based on the history till now, okay, so what is happening here is the global net CO2 emission is being increasing like anything. You can see that we have want to try to slow it down, but if it is continuous without anybody commitment, without any action plan, rather than promises, it's not like election promises, right? So different country nations, people have met in a Paris meeting, and they all of them have pledged that definitely they will do their contribution to reduce the CO2 emission. It may be in different forms. Whatever industry, if you look at transport industry is a major industry which is emitting CO2. Next to it, we are having cement industry. So these two are the largest CO2 emission categories. That means that in these two areas, the government has to work. They have to change their strategies to reduce the CO2 emissions. Okay. So otherwise, what will happen? It is going to increase. It will increase by 2050 and 2100. But if you want to decrease the compatible temperature increase is only 1.5 degrees Celsius increase. So if you want to consider that, if you want to have a compatible path we want to follow, so this trajectory has to be brought down. Okay. So what is that? So this is the historical data. By 2100, with the current government policies, there may be increase in 3 degrees Celsius, 2.7 to 3.1 degrees Celsius of temperature increase is projected. As per our present scenario, means we are assuming that there is no new addition here. So whatever new productions are there in countries, it will be done using greener technologies. So there won't be any addition of CO2 emission further. In that case, we are assuming this is the projection up to 2100. Okay, now we are in 2022. Okay. So this is what we have been committing. So several governments have committed that they have given some pledges and they made the target. Even our Indian government also has made some pledge. We are also committed towards reducing the CO2 emissions. Okay, so we are increasing our investment in fuel cell technologies. We are giving hydrogen economy preference over crude oil economy. So all that we are going to discuss later. Okay, so like that, every country has given pledge and promise to reduce the CO2 emissions, which will reduce the increase in temperature, global warming to 2.4 degrees Celsius by 2100. Okay, so that's what if you are assuming some optimistically, let us say that every industry has changed their strategy, so net zero targets is achieved. In that case, we are going to have a temperature increase of 2 degrees Celsius. Okay, so that is what is being expected. So that is, we can have around 2 degrees C consistency is maintained. So we can have that if you are maintaining 1.5 degrees Celsius consistent, so then we can have a projection which can go down up to 1.3 degrees Celsius. So this are the different things. It's like when we are successful 100%, we will be able to reduce it drastically, but if at least if we are 50% successful in our target, we will be able to reach this. So that is the target being done. Okay, so we want to reduce the CO2 global GHG, greenhouse gas emissions in gigatons CO2 per year. Okay, so that is being reduced like this. Okay, so all this will help us to reduce the global warming. Okay, so that is the objective behind this thing. So if you look at the nations' commitment, different nations have committed, as I told you, at least 73 nations have committed for net zero greenhouse gas emissions by the year of 2015. creating a major challenge for the cement industry. As I told you, this is the second largest industry sector which is emitting CO2 next to the first one, largest one is transport sector. Okay, so cement industry is one where we have to focus on to reduce the CO2 emissions. If you want to, whatever promise that India has made in the global meet, we want to reduce the greenhouse gas emissions to net zero by 2050 year. So switching the fuel supply to zero emission sources will only address around 25 to 40 percentage of greenhouse gas emission associated with the cement making, since the majority of the CO2 emissions are process based coming from the limestone feedstock. So if you are changing the technology, it will only reduce up to 25 to 40%. But if you look at the feedstock based thing, so that emission is majority. Okay. However, there are a lot of effort is being made to reduce both the process and the energy emissions, and they are limited to developing new kind of cement, replacing the cement or concrete with other construction materials, or by incorporating carbon capture and storage into the plants, making the clinker that accounts for around 70% of most type of the cement. So how we can capture the carbon dioxide that is being formed from this cement industry? So there are several solutions are there. So the several technologies that are available for carbon capture are amine scrubbing. It's like our absorption. We can absorb that CO2 into some liquid and store it, or into some absorbents. We can store it. Or we have calcium looping. We have chilled ammonia. We have electrochemical separation, converting CO2 into some useful chemicals, or metal oxide sorbents, and oxy-combustion. So these are several technologies that are available to capture the carbon dioxide that is formed or emitted from the cement industry. Okay. So in this regard, we have molten carbonate fuel cell having a significant role to play, because in the cement industries, if you are going to install some molten carbonate fuel cells, what they can do is they can use the CO2 as the raw material. They can use it as a fuel cells, which is made of carbonate or molten carbonate. They can use the CO2 as the fuel. So that is the reason behind we are talking about the cement industry with this particular lecture on molten carbonate fuel cells. So these molten carbonate fuel cells have recently been identified as another powerful technology which can easily capture the CO2 from the flue gas that is being produced by coal or natural gas fired power plant, or even from the cement industries, because they have the advantage also generating very low carbon base load electricity and high grade waste heat that could be utilized for, because the reaction that is taking place here is endothermic, which we are going to discuss in detail. So for this endothermic reaction means we have to supply heat, right? So that heat is being supplied from the waste heat that is produced from the fuel cell. So thereby the technology needs a very less complicated units. So we don't need an external steam reforming unit to convert the hydrocarbon fuel into hydrogen. So internally, because we are operating temperature is more than 600 degrees Celsius, so what will happen is whatever hydrocarbon is coming, that steam reforming reaction, water gas shift reaction, all that will take place within the system. Okay. So they will be used to produce more power using the steam turbines or the organic Rankine cycles. Okay. So the cost of the CO2 capture from the coal and natural gas fired power plants using this molten carbonate fuel cell is estimated to be around $25 to 100 per tons of CO2 avoided. The studies assumed that natural gas is being reformed to hydrogen in the anode of molten carbonate fuel cell. As I said, because of the high temperature, operating temperature are more than 500 to 700 degrees Celsius. So all this steam reforming is being taking place within the system. We don't need an additional separate unit for steam reforming. Okay. So that is the advantage of this molten carbonate fuel cell. So that is where we are coming into this today's lecture, where we have high temperature fuel cells. Within high temperature fuel cells, we can classify them as intermediate temperature fuel cells and very high temperature fuel cells. So when I say intermediate, it is again in the range of 500 to 700 degrees Celsius. Okay, and if you talk about very high temperatures, it is around 700 to 1000 degrees Celsius. So today we are going to focus on this molten carbonate fuel cells. Remember, when I say high temperature fuel cells and their operating temperature is high, do you think they can be used in our transport vehicles, in our car or two-wheeler kind of thing? No. So that itself, when the name we are saying about high temperature fuel cell, it tells us that it is mainly useful for stationary applications like apartments or buildings or a campus or a military bases, all these places, this can be utilized. Okay. So coming to this molten carbonate fuel cells, the reaction that is going to take place in this molten carbonate fuel cells can be given here. So this molten carbonate fuel cell means that we are going to have some salt, whatever salt, it can be sodium salt or potassium salt or any other salt. So carbonates of sodium or potassium can be used. Okay, used as the electrolyte. So they all are in molten carbonate. When I say molten carbonate, because the operating temperature, this is around 600 degrees Celsius average, they are all, this carbonate salt will be in the liquid phase. That is why this is simply, we can simply call the CFC, carbonate fuel cells, or sometimes it is mentioned as molten carbonate fuel cell. Both represents same. Okay, so that we should know. Carbonate fuel cells or molten carbonate fuel cells. So where this mixture of sodium carbonate, potassium carbonate are being used as the electrolyte. Okay, and these electrolytes, what they use, they can be taken in a ceramic base. These liquids will be filled in the capillaries of this porous ceramic membrane, and in both sides we can have anode and cathode. Okay, so in both sides we'll have anode and cathode. So what we'll have is, we don't need, because this high temperature, we don't need any costly catalysts are not required, or costly and I say precious. Precious catalysts are not required. That is, what is that? Precious catalyst means platinum, palladium, gold, kind of costly catalysts are not required. So it is enough if you use some transition metals like nickel. Okay. So porous nickel catalyst is sufficient. So that's a very cheap material, because it needs only a surface for the reaction to take place. Okay. So in these molten carbonate fuel cells, what we have is, at the anode we are going to supply hydrogen and carbon monoxide. Okay, so hydrogen and carbon monoxide are being supplied. When I say that, it can be a syngas, okay, or any in different composition, it can be whatever composition. So these two are being used as the fuel or raw material, right? So the raw material here is hydrogen and carbon monoxide. Okay. Well, the raw material here is carbon monoxide and hydrogen is being sent. So what they do is, this hydrogen and carbon monoxide will react with carbonates. So this hydrogen and carbon monoxide will react with carbonates to produce water, CO2 and electrons. So that will be the reaction. So what is the reaction taking place at anode when you use hydrogen and carbon? Remember, it can be pure hydrogen also you can use. So fuel can be, first case only hydrogen, second case it can be hydrogen, carbon monoxide. So for second case, what are the reaction taking place is, so this hydrogen will react with carbonate to form H2O plus carbon dioxide plus electron. And what this carbon monoxide will do, remember, that is the advantage of using this molten carbonate, because when you talk about these high temperature PEM fuel cells, catalyst poisoning is a big issue, right? Carbon monoxide is there, means catalyst poisoning will happen, so the membrane will degrade, all that, right? So that is here it overcomes that. Even the carbon monoxide is consumed in this reaction, where CO plus CO3 minus will form CO2 plus electrons. So if you balance it, it is 2 CO2 and 2 electrons. Okay. So this is the reaction taking place at the anode when you are using these two fuel. If it is only this fuel, only this reaction will take place. First case. In second case, this A and B will take place. Okay. So reaction 1 will take place. In this case, reaction 2A, 2B are taking place. Okay. The products being formed are the products that are formed at this anode are water and carbon dioxide. Okay. So what is taking place at what takes place at cathode? Remember, we don't need any precious catalyst in the cathode side also. So what we will be supplying? The raw material oxidant. What is that? It can be oxygen or air. Okay. So what is the reaction taking place at the cathode side? Reaction taking place at the cathode side is you have oxygen, you have that CO2 formed in the other side will come to this side, CO2 plus the electron will come through external circuit, right? Electrons at anode will come, right? So this electron has to come through the external circuit, so that electron also will be consumed to form carbonate. So this carbonate is being formed, so balancing it, so we will have 2 CO, so that 4 electrons that is going will come. So what is that? This oxygen is reacting. What is happening at the cathode? Oxygen is reacting with CO2 and electrons to form carbonate ions. So here only we are getting carbonate ions production. Okay, so carbonate ion is being produced at the cathode with the CO2 being formed at the other side, because we have seen that here CO2 is being formed, water is being formed, right? So this is the reaction taking place. So the overall reaction that is taking place, overall reaction, right? We know that in any electrochemical reaction, anode reaction, cathode reaction, balancing it, you will have overall reaction. Okay. So what is the overall reaction here? So H2 plus CO2 plus half O2 gives H2O plus CO2. Okay. So this is what takes place when there is only hydrogen is taking place. When you have only hydrogen, so this is the overall reaction. Okay. But when you use hydrogen and CO, the overall reaction is not this. You will have H2 plus CO plus 1 mole of oxygen will react to form H2O plus CO2. So this is our overall. This is our overall reaction. This is our overall reaction that is taking place when you use hydrogen and carbon monoxide as the fuel. Okay. And what is the electrolyte? It is a mixture of sodium and potassium carbonate supported by the ceramic matrix. So I told you the electrolyte being used is here is sodium and potassium carbonate supported by a ceramic matrix. Okay, so that is the electrolyte we are using here. So based on the electrolyte name, the name of this fuel cell is molten carbonate electrolyte. That's it, no? Molten carbonate fuel cells. Okay, if you remember, if the electrolyte is membrane, it is polymer electrolyte membrane fuel cells or proton exchange membrane fuel cells. If the electrolyte is an acid, then it is phosphoric acid fuel cells. If the electrolyte is alkaline, we have alkaline fuel cells, right? So based on the name of the electrolyte being used, the name for each fuel cell comes into picture. Okay, so with this backdrop, so that is the reaction that is taking place, which you can see here. Okay, so what is happening here is this carbon monoxide plus water will form hydrogen plus CO2. you will have methane. If you are using methane also, methane plus water will form hydrogen plus CO2, which is called as steam methane reforming. So then we have carbon monoxide whatever is present. So carbon monoxide plus water will form H2 plus CO2, which is called as water gas shift reaction. So these two are actually, if it is not a low, if it is low temperature fuel cells where we are supplying these light syngas as these raw material, this unit will be taking place outside. Okay, these two steam reforming followed by water gas shift reaction, then followed by carbon monoxide removal, all that will be then, and the pure hydrogen will be sent into the fuel cell. So that's what happens in a low temperature fuel cells, but it is a high temperature fuel cell. When I say high temperature, the operating temperature is around 500 to 700 degrees Celsius or molten carbonate fuel cells, or it is more than 800 to 1000 degrees Celsius for solid oxide fuel cells. So in both cases, for stationary applications, we can use these high temperature fuel cells. Okay, so this separate unit of steam reformer and water gas shift reaction and CO removal is not required. Okay, so with this case, so this takes place nearby the anode surface ready-made. Okay, on this spot, hydrogen is being produced within the system, and that hydrogen is reacting at the anode. Okay, so in the and then the electron formed will be going through the external circuit. This carbonate which is formed at the cathode side is reaching to the anode side through the electrolyte. Okay, so we are supplying oxygen, either oxygen or air plus flue gases, whatever, because the mixture is sent. So we will be getting CO2 lean stream from the cathode side, CO2 rich stream from the anode side. Okay, remember CO2 is being formed in the anode side as we have seen the reaction. Okay, so those are the generalized chemical reactions that are taking place in a fuel cell, which you can see here again. So this is a typical diagram for if you are asked to draw a line diagram for molten carbonate fuel cell, you have to make this drawing. Okay, so you are a sandwich, right? Always it's electrolyte, anode, cathode. Even MEA membrane for even that electrolyte is membrane. MEA assembly was done with like this only, no? So you have the same setup here. Here the electrolyte is a ceramic matrix which is saturated with a particular mole basic percentage of sodium carbonate and potassium carbonate. Okay, so at this operating temperature of 600 degrees Celsius, they will be in liquid phase. Okay, so that is molten phase. Okay, so that way this electrolyte is there which will facilitate the carbonate ions passage. At the anode, we are supplying hydrogen, means the reaction taking place will be hydrogen plus carbonate will form water and carbon dioxide. So that way the gas that is leaving this anode side will be CO2 rich gas stream. Okay, so therefore electrons are being produced which will go through the external circuit and reach this here, which will be taking part in the reaction taking place at the cathode side, where we will be supplying oxygen. Okay, and whatever carbon dioxide formed, some can be recycled here. We don't. So that way the CO2 is being, CO2 and oxygen reacts to form carbonate. Okay, so that is the reaction takes place when you are supplying pure hydrogen and oxygen along with carbon dioxide in the cathode side, hydrogen in the anode side. Okay, so that we should be clear. And if you know that what are the general electrolyte which are being used, so you can use lithium carbonate, sodium carbonate or potassium carbonate. Okay, so what is the difference? We will see that which one is more effective. A lot of research is being done, and such way this electrolyte is being used. So in a molten phase at 600 to 800 degrees Celsius, this molten carbonate fuel cells is operating at a high temperature of 600 to 800 degrees Celsius, which mostly uses the molten carbonate salt as an electrolyte, where the salt can be lithium carbonate, sodium carbonate or potassium carbonate. So the reaction taking place already we have discussed, and this technology is being developed in the 20th mid of the 20th century. Okay, 1960, 50 onwards, a lot of research is being done. where people focused on using it as an electrolyte, means using carbonate as an electrolyte, because wherever other type of fuel cells, we had the issue of CO poisoning, CO2 poisoning, all that, right? So there is a lot of tolerance to CO is not there with membrane fuel cells. So people started working to explore what if you use some electrolyte which will be very much close, or which can even use the carbonate, carbon monoxide as a raw material, as a reactant. Okay. So using this type of carbonate electrolytes, which eliminated to regulate the carbonate buildup in the system, we are having is molten carbonate fuel cell. As I told you, it's made up of a electrolyte, which is usually a matrix, ceramic matrix or lithium aluminum oxide matrix. And we have electrolyte, which can be in molar basis of 62%, 38% lithium carbonate or potassium carbonate, like that. Even sodium carbonate can be used. Okay. So different people use different electrolytes. Okay. So this type of salt at the 600 degrees Celsius, I told you that they will be in molten state, which will even occupy these spaces, and even they will diffuse even to the pores of the nickel catalyst also. We are going to have a nickel oxide catalyst. You can say that recently, instead of nickel oxide, lithiated nickel oxide, which is having a pore size of 7 to 15 micrometers, porosity of 70 to 80%, which facilitates this carbonate to reach the active sites of the catalyst. Okay, even in the anode or cathode. Okay, so you are having nickel 10% with 10% chromium is being used as the anode. Pore size, porosity around 50 to 70 percentage. Okay, so the thickness, you can see they are just thickness, 1 thickness, 0.5 thickness, like that. Okay. Then as usual, at the end we are going to have bipolar plates to facilitate the flow field. Okay, that is supply of your raw materials, hydrogen or oxygen. So we'll have bipolar plates. Okay. So this is actually what happens in a molten carbonate fuel cell. So we have discussed about the reaction that is taking place. This molten porous anode can be nickel with chromium or aluminum. Cathode can be a lithiated nickel oxide. Mostly the molten electrolyte which is being used are lithium carbonate, potassium carbonate mixture. Okay. So the major product being formed are hydrogen, water and carbon dioxide in the anode side, where the electrons will be moving out. Then at the cathode side, whatever coming out, we are supplying oxygen, carbon dioxide, whichever is not consumed here will be leaving from the other side. Okay, so that's what happening in here thing. So we'll look into a small animation also, if time permits. So essentially, the fuel is being treated and the hydrogen is being, this is what happens within the molten carbonate fuel cell system. So fuel is being getting treated here within the system using the waste heat that is supplied, which is being produced during the reaction taking place in the fuel cell, major fuel cell stack. So that heat is utilized to treat, that is a steam reforming, all that will be taking place, where we get hydrogen and carbon monoxide into the system. Okay. So that way it can be like a power generation unit, we can use this. So whatever power is produced from the fuel cell is a DC current, and so we have to need a conditioner where we convert DC current into AC current. That is our desired product, right? So desired product here is electricity. Okay. So DC current is being produced. Okay. Some heat is being there. Some majority of the heat will be utilized within the system, and very little heat is being rejected from the system. So that is a block diagram for this molten carbonate fuel cell, if you understand it clearly. So getting into the history of this molten carbonate fuel cell, so I told you that in molten carbonate fuel cell, they are using molten carbonate salt in saturated into a ceramic matrix, which is being used as electrolyte. So this salt commonly being used are lithium carbonate, potassium carbonate and sodium carbonate. These are the three most commonly used electrolyte for molten carbonate fuel cells. Okay. And if you look at another high temperature fuel cell, which is solid oxide fuel cell, as well as this molten carbonate fuel cell, so both are high temperature device. So that way their development is also followed a similar lines until later the 1950s. Okay, very first in 1950s, first Bohr et al. They did some experiment by using the solid oxide electrolyte. So that is the first experiment done. Okay, for solid oxide fuel cell, they did some experiment in 1950, which they tried to use solid oxide as the electrolyte. But they faced a lot of struggle. They had technical problems. So they encountered were again tackled by Russian scientist O.V. Deveopment, but still he also failed to overcome the technical problem. Okay, so this is what happened in 1950s. In 1960s, Dutch scientists Broers and Kettler, they reported a paper in a journal called Industrial Engineering Chemistry. So they reported that high temperature fuel cell, which are run for 6 months, they tested it for 6 months running by employing an electrolyte, which is made up of alkali metal carbonate and contained within a disc of magnesium oxide. So they used magnesium oxide discs for as a catalyst, and they use these alkali metal carbonates. So they told that reported that the cell operated well above the melting point of the carbonates, and carbonate ion was found to be the means of charge. And that is, they are the first to report what is the mechanism that is taking place, who is responsible for carrying the charge transport within the molten electrolyte. Okay, so that is what the first paper, you can see that journal paper, volume 52, number 4, April 1960, page number 303 to 306. They even taken this diagram from that journal. I referred to it. Okay, so we see that this is what they reported that. So this carbonate ion is responsible for the charge transport within the molten carbon. As I told you, in any fuel cell or electrochemical system, electrons will be passing through the external circuit, and the charge is being passing through the electrolyte. So in the through the electrolyte, we have charge transfer taking place. Through the external circuit, we are having electron transport taking place. Okay. So even though in the past 40 years, there are many changes that has taken place in the material of construction of this MOFC, that is MCFC, that is molten carbonate fuel cell, but the operating principle remains the same what we have discussed, that reaction that is taking place also. Okay, so that's what we have discussed, this the reaction that is taking place. So after their reporting in 1960s, in the mid 60s, even US Army's Mobility Equipment Research Development Center, they tested several molten carbonate fuel cell made by Texas Instruments, where they had even wide range, 100 watts to 1000 watts fuel cell have been made by Texas Instruments. They even tested them, this research center. So this is illustrated schematically in the diagram which you have shown here. So this is what happens in this diagram. One of the characteristics that distinguish this type of fuel cell from all others is there is a net transfer of CO2 from the cathode side of the cell to the anode through the electrolyte. Okay, so here through the electrolyte, we are having the CO2 transfer taking place. Okay, you can see there is passing of CO2 here, right? So that way, the CO2 transfer from the cathode side of the cell to the anode side is taking place. And following this early work in the Netherlands, there is a development of molten carbonate fuel cell, which has attained, many people have joined the research teams. So several university groups and organizations such as Gas Technology Institute in USA and the Energy Research Center of the Netherlands, they all joined in the research area of molten carbonate fuel cells in the late 1960s of this. Okay. So this now this today scenario 2020, this ECN is an international leader in energy innovation. So that is the thing. They have been come a very long way. They are leading the new energy research areas. If you go to their website and search, okay. So that has come a long way to 1990s also. So because remember, when you talk about this high temperature thing, we had a limitation of material that is suitable for high temperature application. Because high temperature means corrosion takes place, lot of corrosion, type of corrosion will take place, right? Rather than the environment, temperature itself a major factor for corrosion taking place, right? So that way, this development of a good material of construction has helped. Then, so that limitations has been well established. Okay, so by 90s, the material of construction had become well established and the limitations were understood. What precautions we have to take, we have to include chromium into the nickel, like that. So whatever it is, either the material of construction is for catalyst or the electrolyte or the system, it has been understood, well understood. You look at this Ishikajima Heavy Industries, which they from Japan, they showed in 1980s, 90s that a 100 watts my molten carbon fuel cell power generator can continuously operate without getting any problem, at least for 10,000 hours. So they did the research and they did the experiment and they have tested it that they are able to run a molten carbonate fuel cell without any problem for 10,000 hours continuously. And then larger power plants with outputs of even 3 megawatt things have been already planned, and there are a lot of industries are being there with molten carbonate fuel cell. Okay, so although these materials costs were relatively low compared with other fuel cell types, there were major problem associated with the degradation of the materials and the poor lifetime of the molten carbonate fuel cell. So that is the challenge or limitations we can talk about later. So at this stage only, the research was focused in three main areas. People started working in three main areas. So people started working to what kind of material has to be selected so that we can increase the operating life of the cell. So how we can do that? We can do by improving the electrolyte and its support and reduction of the electrolyte losses during the operation. So then they did scale up of stacks in system design to maximize the benefit of internal reforming. So these are the research areas people have worked in this molten carbonate since 1990s. So R&D is in these areas. R&D, when I say it's a research and development in all these areas, continues, and with commercialization of this technology being pursued in the three major countries are USA, Japan, and Europe. Here they are commercialization level. The research has attained some maturity. Okay. And if you look at the earlier days of these molten carbonate fuel cells, the electrode more often than not employed were only platinum type of precious metals. But once the technology is developed and very good research has been done, now it was found that nickel itself is sufficient. It's adequate both as the metal for anode as well as oxide metal for cathode. So nickel oxide is used as for cathode. Nickel as a metal is used for the anode. So this porous nickel with the porosity percent we have seen 50 to 70% porosity, which helps the carbonate to reach the anode surface and react also. Okay, so for this electrolyte, most developers have been adopted a eutectic mixture of lithium and potassium carbonate. When I say eutectic mixture, the percentage is fixed. Okay, 62% lithium and 38% potassium. They form a eutectic mixture. So they have a melting point of around very high temperature, 550 degrees Celsius. So that is the reason to choose this particular composition. So this mixture is usually impregnated into a porous solid support matrix made up of lithium aluminate. So lithium aluminate also can be used, or even ceramic. Recent days, ceramic is being used as the support matrix. Okay, so preferably lithium aluminate is being used as the support material for this molten carbonate fuel cells. Okay, so for molten carbonate fuel cells, what is the preferred support matrix? It is lithium aluminate. Okay. However, since both the anode as well as the cathode need to be porous to allow the reacting gases to reach the electrode or electrolyte interfaces, the pore structure of the cell component needs to be very carefully controlled so that we don't have much loss of the electrolyte. What is electrolyte? This eutectic mixture. Okay. So unlike other type of fuel cells, this molten carbonate fuel cells relies on a balance in a capillary pressures within the pores of the anode as well as the cathode to establish the required boundaries. That is the interfacial boundary between the electrode and electrolyte. Okay. And if you look at this construction, it is invariably of planar construction, and each of the porous component is normally made by tape casting method. This is a technique used for making the porous catalyst. Okay, and this has enabled the significant scale up to achieved, and the cells of even 1 meter square area is being routinely manufactured. So from 1 centimeter by 1 centimeter length, We are able to make 1 meter by 1 meter. 1 meter is you can see that, right? So 1 meter by 1 meter cross section area electrolyte. This thing has been done. Okay. So the normal operating temperature is around 600 to 700, means that this when I say cells, it is fuel cell, not the things. Okay. So these fuel cells can be held together in a housing made up of stainless steel in case KC. Okay. A particular issue is that of ensuring gas tight seals around the each cell. That is a challenge there. Obviously, we want to have a gas tight seal, and this can be achieved by using a liquid molten carbonate to form a wedge seal against the metal cell housing. So that is also being addressed. Where the carbonate is in contact with the metal, corrosion is likely unless the metal is protected. So for this, to achieve this, what we have done, a coating of alumina is normally employed. So that way, every challenge needs to be addressed by taking care of understanding it first and then using some solution for it. Okay. So if you look at the history again, in the early 1990s, it was found that using a eutectic mixture of lithium carbonate or potassium carbonate, electrolyte segregation being taking place, which can occur both within the fuel cell as well as in the stack. So in the cell, the segregation, what will do? What the segregation will do? The segregation will increase the potassium concentration near the cathode, which leads to increase the cathode solubility. That means what? Corrosion of the cathode surface. Corrosion is cathode material is soluble into this solution. Okay, so that is taking place. And what will happen when the cathode is getting soluble? We are losing the structure. What will happen? Obviously there will be decline in the performance because there will be more polarization losses. Okay, so the chemical kinetics will be slowed down also. So in the stack, what will happen? It was found that the electrolyte segregation can lead to a severe decline in the performance of the end fuel cells within the stack. So within 100 fuel cells present in a fuel state, the end fuel cells tend to have very poor performance. Okay. All these observations, particularly the issue of this cathode dissolution into the electrolyte, which has been addressed by the researchers, and in the late 90s they did a lot of research to find some alternative electrode material. Okay, and that's why they have so many material combinations of lithium sodium potassium or lithium potassium or sodium potassium carbonates at the same temperature. So they can do some study, experimental study, and among these they found that lithium sodium should exhibit a high ionic conductivity compared to these three. Okay, so they did test with these three and found that this combination lithium sodium is better than lithium sodium potassium or lithium potassium or sodium potassium carbonate mixtures. Okay, so that way this lithium sodium is being used as the preferred electrolyte. Okay, and several researchers have even verified that work. Morita et al. Have been they have verified it also. Then Tonimoto et al. Also carried out a series of laboratory scale experiments with the fuel cell using lithium, sodium, and potassium carbonate electrolytes. They also find even the investigated by adding some of the materials like calcium, strontium, barium to the material. So they added certain percentage of them, and I studied whether how it improves the or how it suppresses the cathode material solubility in the solution also. Okay, so this nickel oxide is less soluble in sodium carbonate and potassium carbonate, and therefore this lithium sodium carbonate should be better as an electrolyte than the lithium potassium in terms of cathode dissolution. Okay, so that problem is being taken care when you are using a combination of lithium sodium carbonate than other combinations. Okay, and this has been even again tested by the recent work by Mitsubishi, who examined the cathode current collector and electrolyte of the cell that had run for extended periods with these lithium sodium electrolytes, and a lot of research is being done. In 1997 a molten carbonate fuel cell power plant in San Diego, California was done by MC Power company. Okay, so there was a power plant in 1997 came into picture. And whatever electrolyte that conducts carbonate ions, it is necessary to provide carbon dioxide additionally to the oxidant at the cathode to form the carbonate. So we are supplying carbon dioxide. So this doesn't mandatorily mean that CO2 should be supplied externally. It can be recycled from the anode side also, because we have seen that you have CO2 being formed at the one side. Okay. So these high operating temperatures of such fuel cells will allow us that internal processing of the hydrocarbons, such as I already explained you this, such as natural gas, which can take advantage of already existing production facilities and the delivery infrastructure for the fuel. So the residual combustible anode of gases from the internal reforming process can be burned in a burner chamber of the gas turbine, and that heat also can be used. Okay, so that way this molten carbonate fuel cell is suitable for inclusion into a combined cycle or hybrid cycle power plants. And these molten carbonate fuel cells also employ low cost metal catalyst because it doesn't require any precious metal catalyst like platinum. So they just need a nickel for the activation of the reactants. So they are less prone to carbon monoxide poisoning due to the same reason being the high operating temperature for molten carbonate fuel cell. Okay, so we are not using any platinum, which may be having a CO poisoning problem. So that is the reason when you use nickel and at even at 650 degrees Celsius, we are we are not having any problem of CO poisoning, which may occur for platinum at this temperature. Okay. And furthermore, we are getting around very good electrical efficiency than phosphoric acid fuel cells. Even we are getting around 60% efficiency, electrical efficiency. And it can also even increase when you do combined heat and power generation. We are going to discuss that separately also. In a unit, waste heat, everything is recovered. Say for heat is there, it is being utilized. We are producing water, which is being utilized. We are producing electricity, that is our desired product, right? So overall, so by calculating just in fuel cell, you calculate only current efficiency, but the heat is being generated. Can you use it? Can you run something and do it and say that some percentage that we can have something useful? Then the overall efficiency, we can talk about overall efficiency because we are utilizing the heat to further produce, or we put a cost for that heat which is being utilized. Okay, so thereby we can increase the overall efficiency up to 85%. So the overall efficiency of an 85% is possible when you use that combined heat and power generation. What is that? Combined heat and power generation. When you perform that, we are getting an overall efficiency of around 85%. Okay, so that is the advantage of this molten carbonate fuel cell. But however, this technology has some low energy density than the PEM fuel cell, which means that it requires some good system of thermal management, and the electrolyte is very corrosive, lowering the lifetime of the stack. Also, it has an issue of long startup time because long startup time means what? Instantaneously it won't start working, right? The carbonate has to be formed, it has to reach the surface, right? So then only carbonate is acting as your electrolyte. So that way there is an issue with the long startup times. Once initially means from shutdown to going to steady state, it takes a lot longer time. That's what long startup time means. Okay, and what type of source of heat to use to initiate the startup process also an important, right? So remember the heat to run the thing, we have the heat internally generated because exothermic reaction is taking place in the fuel cell. So to initially how to light it, right? So that is the thing here. So that also has to be done, right? So nowadays what we are doing is a new tubular fuel cells are being designed with better stability and robustness, higher energy density and longer lifetime. So thus making this molten carbonate fuel cell to be more sustainable in the future. So that was reported in 2017 by Kawase et al. Okay. So these molten carbonate fuel cells are applied in large stationary power generations, where we can even have power output of even 200 kilowatts to few megawatts also. Similarly, these phosphoric acid fuel cells also being researched for implementation in the ship in hybrid cycle with a gas turbine or an internal combustion engine. Okay, so phosphoric acid is being currently used, and people are looking to replace it with molten carbonate fuel cells for ship also. Okay, these molten carbonate fuel cells, as we have repeatedly telling, it is average temperature is around 650 degrees Celsius, and there are several advantages associated with it. Firstly, the high operating temperature dramatically improves the reaction kinetics. The first reaction kinetics is the major advantage with this, and it doesn't require any necessary to boost these with any costly, noble, precious metal catalyst. And this high temperature also makes the fuel cells less prone to carbon monoxide poisoning than the lower temperature systems. And because of this, molten carbonate fuel cells, which can operate out a variety of different fuels, not just hydrogen. You can use methanol, you can use methane, you can use any other hydrocarbon, you can use even syngas, flue gases, like that. Any combination you can make use as the fuel in the molten carbonate, because it doesn't require any external steam reforming unit when you are using hydrocarbon. Okay. So when you say the different fuels, variety of fuel, it includes even coal-derived fuel gas, methane or natural gas. So thereby it doesn't require any externally steam reformer, where the steam reforming and water gas shift reaction needs to be carried out if it is a low temperature fuel cell. So in molten carbon fuel cell, which is operating at 650 degrees Celsius, we don't need a external steam reforming unit. That is the word you have to underline. Okay. So we have already seen the reaction that is taking place. So in comparison to other fuel cells, you can see in molten carbonate what are the reaction that is taking place. And we have seen already the lithium carbonate and sodium carbonate being used as the electrolyte. So here the current charge carrier. What is the charge carrier? Carbonate ions are the charge carrier from the cathode to anode direction. The direction also here H plus ions is the thing in case of a fuel cell. In case of acid fuel cell, phosphoric acid fuel cell, where H plus will be moving from anode to cathode. Okay, but here from cathode to anode, carbonate ions are being passed. Okay. And in most of these cases, the electrolyte of this molten carbonate fuel cell is made up of lithium potassium carbonate or lithium sodium carbonate salts, which is heated up to 600 to 1000 degrees Celsius. That is operating temperature for the fuel cell. And at this temperature, as I told you, the salt is in liquid phase, and they can conduct ions between the two electrodes. So you are going to have carbonate ions, which is formed at the cathode, passing to the electrolyte and reaching the anode site, where it reacts with the hydrogen or other things. Okay. So this particular mixture of this carbonate salt melts at 550 degrees Celsius. When you use this Utetech mixture of 60 to 38 percentage mole percentage of lithium carbonate and potassium carbonate, they have each one. Say when you use lithium carbonate and sodium carbonate, they will have one salt will melt at a point, right? Melting point. Accordingly, we have to use it. So that lithium aluminate is being there. We can use a ceramic matrix retaining the molten salts. It can be used both as an ion conducting electrolyte, also as a gasketing for the fuel cell stack. I told you which is responsible of conduction of the charge. Negative carbonate ions, that is CO3 2 minus, is responsible for the charge transfer. The long-term performance is a big issue for molten carbonate fuel cell, as we have discussed. Okay, and if you look at the performance of these fuel cells, I'll briefly introduce the performance of the. So, what are the properties that account for the electrolyte performance? While choosing the electrolyte for this molten carbonate fuel cell, if you look at the volatility of different alkali metal hydroxide generated in the moist cathode atmosphere, particularly the solubility of the cathode, segregation of the electrolytes, both oxygen and carbon dioxide solubility in the electrolyte, oxygen reduction kinetics have to be taken care. Okay. So how the loss of electrolyte is taking place at the cathode via it is through hydrolysis. So this is what happening with respect to this thing, plus water forming 2 methanol plus CO2. So this, especially this electrolyte that has been used unaltered for long time is your 3862 lithium potassium tech mixture. So what causes is they have a relatively high volatility. So with respect to performance over a long period, it causes the fuel cell to dry out because the partial pressure of methanol varies with square root of water vapor to carbon dioxide vapor pressures as given in this equation. So you have KIT. KIT is the equilibrium coefficient of the carbonate ion in the melt according to the equilibrium equation. You can see the carbonate plus water forming reversibly CO2 and OH minus ion. Okay. The anode off gas, on the other hand, can be mixed with the air after combustion and reused in the cathode chamber with a sufficiently high air, excess air. So you are going to have oxygen and carbon dioxide which are being consumed in the ratio of 1:2 by the cathode process as per the stoichiometric requirement. The change in composition of the electrolyte due to segregation and the volatility of certain species may result in the change in the melting temperature. Okay. So that way this electrolyte can solidify, which can cause the fuel cell to malfunction, sometimes allows us the gases to break through, right? So carbonate ions from the electrolyte are used up in the reactions at the anode so that we do have to compensate for the loss by injecting carbon dioxide at the cathode. That's what we have to do. Okay, and there is one Kemla effect. What is that? The Kemla effect is finding that the internal mobility of larger cation can be higher than the internal mobility of the smaller one at the low molar fraction of the later. Okay. So because we know that recent studies have shown that using sodium instead of potassium can decrease the amount of segregation because in a molten binary salt with a common anion, segregation occurs due to difference in the mobility of the cations. This heavier and the bigger potassium and the sodium cation is faster lithium in the mixture that have a higher potassium concentration of 0.32. So we are having the Kemla effect. Whereas below this isotoxic concentration, lithium is faster. So this segregation problem needs to be addressed by the researchers. So the partial pressure of carbon dioxide has a much smaller effect on the current volt curve than the partial pressure of the oxygen. Even we have seen that mass transfer limitations are not observed for CO2, but for oxygen, it is observed at low partial pressures. And if there are transport of CO2, it hinders the cathode operation much less than the oxygen transport, since this gas has a much better solubility in the carbonate melts than oxygen. So these are the reactions corresponding to external fuel cell processor not required for the system. So internal reforming includes that converting, if you are using methane as the fuel. So when you are using methane as the fuel, so these are the reactions taking place which you can go through. Okay. So obviously we are going to have carbonate formation at the one side. Okay. And there are a lot of advantage has been done with respect to molten carbonate fuel cell is that we don't need any non-noble metal catalyst. We need non-noble metal catalyst. We don't need a precious catalyst. So at high operating temperature, you have nickel anode and the nickel oxide cathode will be able to promote the required chemical reaction, electrochemical reaction that is taking place. Which means that we need a low production cost for these molten carbonate fuel cells in comparison to low temperature fuel cells, where the catalyst electrode is usually made of platinum. And these nickel electrodes are less prone to CO poisoning. Okay, so you can see that solubility of electrode in the electrolyte also when you use the different composition of lithium, sodium or lithium potassium. So we have another problem with respect to this electrode, ostward ripening. So the main problem with the electrode in the molten carbonate fuel cell is the solubility in the electrolyte by ostward ripening, which is nothing but a dissolution or reprecipitation process. It decreases the internal surface of the porous nickel oxide cathode, causing it to deteriorate. So the solubility of nickel oxide is dependent on the cathode potential and temperature. The solubility of nickel and nickel oxide in lithium or sodium was found to be lower than that in lithium or potassium melts. Although these lithium sodium melts have been found to have superior performance compared to lithium potassium melts, the lower oxygen solubility reduces the cathode performance on the lean gas with a low oxygen partial pressure. Okay, so we'll just discuss about the advantages and disadvantages. So we have already discussed. You can able to list out what are the advantages that with respect associated to molten carbonate is whatever we have discussed. We can have overall efficiency up to 80%. We have internal reforming taking place. No need of external reforming unit. It doesn't require noble metal catalyst. There are no negative catalyst poisoning effect of carbon monoxide or carbon dioxide. Okay, so this is supporting your spontaneous internal reforming of the hydrocarbons, and they produce some high grade waste heat which is being utilized for converting these steam reforming reactions. All that the reaction kinetics is very fast. Hmm? Right, so that have been discussed, and obviously we have to discuss about some of the disadvantages associated with the molten carbon fuel cell. It is using a liquid electrolyte rather than a solid electrolyte, which introduces liquid handling issue as usual. Say PEM electrolyte, what is the advantage? It can be kept in any angle, all that we discussed, right? So that way when you use a liquid electrolyte, obviously you have some restrictions. The requirement to inject the carbon dioxide at the cathode side as carbonate losses or carbonate is being consumed in the reaction occurring at the anode is one of the disadvantages. And we can look at it other way. We are using in the world there is lot of CO2 emissions. Supplying CO2 emissions will help us to control the CO2 emission into the atmosphere, right? So that we can every problem we can find one of the opportunity also, right? So this it faces since operating temperatures are very high, obviously corrosive nature. When there is mishandling of the things, we are going to have more corrosion taking place. And remember, these molten carbonate fuel cells have very high intolerance to the sulfur. So when you talk about flue gases or any coal gases coming now, sulfur content should be very low in it. The ppm level of sulfur components, either H2S or COS, it should be 1 to 5 ppm, less than 1 to 5 ppm. That we have to take care. Okay, and it requires a considerable warm up period. That's what startup time is required for this thing. Okay. And if you look at the applications, these molten carbon fuel cells are used in large stationary power generations, and most fuel cell power plants of megawatt capacity use these molten carbon fuel cells, and they work with combined heat and power units, CHP units, or we call it a CCP unit, which is combined cooling and power plant. In all these places, these high temperature fuel cells like molten carbonate or solid oxide fuel cells are preferred, and they can work with the efficiency of 60% efficiency to electricity conversion, and when it is operated in cogeneration units, they can provide us around 80% efficiency. Okay, so we know that any fuel cell's performance is a function of pressure, temperature, whatever the composition of the reactant gases, and how the fuel utilization is being done, what type of fuel is being used, and what are the impurities that are present in the fuel, right? And if you look at the effect of pressure, generally, increasing the operating pressure of this molten carbonate fuel cell will result in enhanced voltages, because there will be increase in the partial pressure of the reactants, there will be increase in the gas solubility, and there will be increase in mass transport, right? Because the more gases are dissolving into your system, so there will be more reactant available at the reaction sites for the reaction to take place, right? So there will be more increased mass transport, and there will be more reaction taking place. Okay, and opposing these benefits of this increased pressure are the effects of pressure on the undesirable side reaction that may take place, because when you have this carbon monoxide with under high pressure, there may be carbon deposition, the 2CO plus C, giving C plus CO2. So you have that carbon formation is taking place, so that will get deposited, block the catalyst surface. Okay, and there will be, if you are using methane, there will be methane formation, methanation reaction may take place with the CO being there. CO plus hydrogen will form methane and water. So that may be the side impact of this increasing the pressure rather than the other benefits that we are having. Okay, so we have some benefits and some demerits associated with it. Okay, because this addition of water and CO2 to the fuel gas modifies the equilibrium gas composition, so there will be formation of methane can be formation of methane is not favored. Okay, so we can avoid it. And also increase in the partial pressure of the water in the gas stream
will help us to reduce the change in the voltage, because delta V is equal to 76.5 log P2 by P1, where this is a function of pressure change, which can be given as this equation. So how the voltage change takes place when there is increase in the pressure. Okay, and it is also found to be valid, this equation, for a wide range of fuels and for pressure range of 1 to 10 atmosphere range. This equation is valid. Okay, so what is the effect of pressure can be given using this equation. Okay, and if you look at the effect of temperature, so what happens when you are increasing the temperature? When you increase the temperature, there will be change in the equilibrium composition. Okay, and if you look at P is the partial pressure computed from the water gas shift equilibrium of inlet gas here, and if you have this B as a cell potential calculated using Nernst equation and cathode gas composition, and you have equilibrium constant for water gas shift reaction. Okay, so this can be looked into this table. Looking at this table, we will come to know how it is changing when we are increasing the temperature from 800 to 1000 degrees Celsius. Okay, you can see that voltage EV is equal to 1.15 at 800, but it goes down to 1.133 at 1000 degrees Celsius. That is, voltage developed is getting decreased. Okay, so that is given here, you can go through it. The changes in the temperature and utilization to affect the cell voltage. What is that? The change in the equilibrium gas composition with temperature. You have the partial pressure of carbon monoxide and water, which will increase at a higher temperature because of the dependency of K on temperature. Change in the gas composition and the decrease in the voltage with increasing the temperature is that E decreases with increase in temperature, where E is the equilibrium electrode potential. So operating cell, the polarization is lower at higher temperatures. Okay, so that's what I have told you. It is at 800 degrees Celsius we have 1.155 equilibrium voltage. At 1000 degree it is 1.133 voltage. Okay, and if you look at what is the effect of reactant gas composition and utilization, you have the voltage of molten carbonate fuel cells, which varies with composition of reactant gases. The effect of reactant gas partial pressure, however, is somewhat difficult to analyze. But in general, you can say that as reactant gases are consumed in an operating fuel cell, the cell voltage tend to decrease in response to the polarization that is taking place. It may be due to activation polarization or concentration polarization, and to the changing gas composition in the system. And these effects are related to actually the partial pressures of the reactant gases. Okay, and if you look at what are the effect of impurities, for example, sulfur is one of the villain for these fuel cells, molten carbonate fuel cell, because the tolerance of this any molten carbonate fuel cell to the sulfur components is strongly dependent upon temperature, pressure, gas composition, cell components, and system operations. Okay, so we have to maintain a less than 10 ppm of H2S in the fuel can be tolerated at the anode side, and however if there is an increase in H2S, there will be some adverse effects, emission of nickel surfaces to block the active electrochemical sites, poisoning of the catalytic reaction sites for the water gas shift reactions, and oxidation to SO2 in a combustion reaction, and subsequent reaction with the carbonate ions in the electrolyte may take place. And if there are nitrogen compounds present in the system, ammonia and HCN do not appear to harm molten carbonate fuel cells in small amounts. However, this ammonia tolerance of molten carbonate fuel cell is reported to be 0.1 ppm. So it should not be greater than 0.1 ppm. Ammonia should not be formed in the system. That we have to ensure. Okay.
Well, in this lecture, we have discussed about the principles of molten carbonate fuel cells, because in this fuel cell, actually molten carbonate is being used as the electrolyte. It says a matrix. What are the cathode material, anode material which are being used in this molten carbonate fuel cell have been discussed. Okay, so what is the performance and durability of these molten carbonate fuel cells have also been discussed in detail. Even though these molten carbonate fuel cells are employed for high temperature application, it is one of the emerging system for high temperature fuel cells. Particularly, this is a preferred electrolyte. Okay, lithium or sodium carbonate composition is used as the preferred electrolyte for this molten carbonate fuel cells. Even though there are some alternative electrolytes like nickel oxide cathode things are there, so they all need some further investigation also. Okay, so usually nickel, porous nickel is being used as the anode and cathode material for this molten carbonate fuel cells. And what is the status quo of these molten carbonate fuel cell have been discussed in this lecture. Thank you so much for joining my classroom. Meet you in the next lecture. Bye bye.